In the previous video, we did a little introduction on metrics, and now we're going to derive the Minkowski metric. And once again, the Minkowski metric is the metric that is appropriate for flat space-time and when special relativity is important. And once again, the postulates are relativity, and that it doesn't matter, the physics is the same for all inertial frames. And the second postulate is that no matter what observer, all observers measure the speed of light to be c. That is what people commonly mean by the speed of light is constant. So to derive the Minkowski metric, we're going to use a simple thought experiment. We're going to create a clock. This clock is going to have two mirrors, and the ticking of the clock is going to be a photon bouncing back and forth between the mirrors. And first, we're going to consider this clock in the rest frame of the clock. So we're going to be observer in the same rest frame. So there's a mirror on top, there's a mirror on bottom, and there's a photon traveling from the bottom to the top. And in the rest frame, this distance, is W between the mirrors. And this photon is traveling at speed c. And it reaches the top in a proper time tau. This is separate. Here, since that's separate, let me make that clear. Let's move this over. And so in other words, we have that c times tau is equal to W. Okay, that's the relationship between c, tau, and W. And once again, tau represents the time in the rest frame of the clock, otherwise known as the proper time. Now we're going to boost to another frame that's traveling at velocity v in this direction. So the mirror, when the photon first leaves the bottom mirror, so this is from the perspective of someone who is watching the clock moving by. So the clock, to be clear, is moving in this direction. So with respect to the clock, the observer is moving in that direction. But just to be clear, we're going to say the clock is moving to the right. Okay, so by the time the photon reaches the top of the clock is moved here. So to this observer, it appears that the photon is executing a path like this. And this observer is seeing the photon travel at speed c. And it will take a time t to reach the top. So c times t is the distance from the bottom of the mirror to the top of the mirror as seen by this observer as the photon travels to. And once the photon reaches the mirror, it will bounce off the mirror and go back towards the other mirror. But by the time it reaches the other mirror at the bottom, it's moved over here. All right, we're just going to focus, just like we were focusing on the upward trip in the rest frame over here, we're going to focus on the upward trip going from the bottom mirror to the top mirror. Okay, and in the time that it took the photon to travel that distance, this distance here, to get to the top mirror. It also the whole apparatus traveled to the right a distance v times time. Okay, So now let's work this out. So and again, you can prove this, but I'm gonna postulate that the distance vertically is still w, that perceived distances that are perpendicular to the motion do not appear to change. It's only distances that are tangent to the motion that appear to change. So this vertical distance is still w, and then we have this relationship c times time and v times time. And so we have a triangle here, and we can just use Pythagorean theorem to connect these two. So c squared dt squared, the hypotenuse, is equal to v squared dt squared plus w squared. All right. So I'm going to rearrange, and we're going to note that dt squared is equal to v over c squared times dt squared, and then we have plus w squared over c squared. All right, I'm just going to collect like terms. We have dt squared times 1 minus v squared over c squared. Those of you used to relativity might notice that that is gamma squared, 1 over gamma squared, in fact. And this is equal to w squared over c squared. Well, if you recall, we have that tau is related to c and w in this way, and that d tau is equal to w over c. That's the time in between the ticks. So this is equal to d tau squared, where the time, that's the time as observed by the observer at rest, and dt is the time observed by the observer who's not at rest with respect to the clock. All right, I'm just going to multiply both sides by a minus sign. It will become clear why I'm doing that in a moment. It's just to preserve some sign conventions. We'll talk more about that in a second. So first of all, we have dt squared is equal to v squared minus 1 equals minus d tau squared. Now, I did a couple of things here. One, you notice that the c disappeared. That's because I replaced Vc, which is an important dimensionless quantity of this problem, the speed divided by the speed of light. I'm replacing it with a dimensionless speed v. Okay. All right, so now we have this relationship, and I'm going to notice that v squared, well, v squared is the magnitude of the velocity, but the velocity is just, change in time, but change in position divided by change in time. So I have that dt squared times, I'm going to rewrite v squared now. Well, v squared is the same thing as dx squared divided by dt squared. Let's do this. Let's rewrite this like this. dx by dt squared plus dy by dt squared plus dz by dt squared. That's the magnitude of the velocity. So in any direction. And then we have minus 1. Then this equals minus d tau squared. Now I'm going to notice, I'm going to pull in the dt squared, and I have that dx squared, because the dt squared cancels with the dt squared in the bottom, plus dy squared, let's make that an actual y, plus dz squared minus dt squared is equal to minus d tau squared. All right, and this is the interval. This is the interval in this situation. All right, and if now I can use this interval and I can read off what is the metric by inspection, but I'm just going to note that in general, eta, I'm going to call the metric something special. I'm going to call it eta alpha beta is equal to dx alpha dx beta, which is equal to minus dt minus dt d tau squared. And by inspection, if the time component is 0, and then x is 1, y is 2, and z is 3, then we have that the Minkowski metric, or the metric for special relativity, I'm going to rewrite alpha and beta, is equal to minus 1, 1, 1, and 1. We have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is the Minkowski metric. This was for a particular, in the interval, in this particular case, we were concerned about time, and that's why we ended up with this minus d tau squared. But in general, we have ds squared is equal to g mu nu dx mu dx nu. Okay.